This is a video about non-geometric backgrounds in string theory. We will define these terms precisely in the following, but naively. These can be thought of as spaces on which a string moves that don't have a geometric interpretation. A basic understanding of field theory is required. I'll try to make it as accessible as I can without distorting the results. In QFT, the word background usually means a set of fields that are present in the theory but whose dynamics aren't part of the theory. For example, we can talk about a fermion which is described by the Dirac Lagrangian moving in a background electromagnetic field. I'll call it EM field from now. We can also add interactions of this fermion with this background field. However, in this theory, we don't include the dynamics of the EM field itself. If we wanted to do it, we would do it by including the kinetic terms for EM field in the Lagrangian. As a contrast, in QED, the EM field isn't a background field because its dynamics are part of the theory. In string theory, by background, we mean a set of three fields, and these three fields are the metric tensor G, a field called the Kalb Ramond field. It's an antisymmetric tensor field and is referred to as B field, and a scalar field called the dilaton field called phi. So a background is defined as the trio, GB and phi. For the viewers who want details, the B field can be thought of as the EM field for the strings, except that instead of being a vector field, it is a second-rank tensor field. It turns out that it has to be the case because the string is an extended object. The EM field for an extended object with p spatial dimensions will be a totally antisymmetric p+1 rank tensor. Two side comments are required here. Firstly, these background fields can be thought of as produced by strings themselves. So, these aren't something that we put in by hand. Secondly, in superstring theory, there are other fields that come into play called the RR fields. We won't talk about them here. GB and phi define a background in the absence of RR fields. Before describing the conditions under which such a background is non-geometric, we have to talk about string dualities. If a transformation keeps the action of the theory invariant, we call it a symmetry of the theory. However, a transformation that changes the action but describes the same physics is a duality transformation. Describing the same physics naively means that the dual theory has the same set of states. The jargon for this criterion is that the spectrum of the theory hasn't changed. In string theory, there are a lot of dualities, but the duality that we will talk about is T-duality. Suppose there is a compact direction in the space on which a string theory is defined. That is, the space contains a circle with a radius, r. T-duality relates physics described in such a space with physics described in a space where this radius is 1 over r. Now, in literature, there are different meanings of a background being non-geometric. Some say that a non-geometric background is a background that can't be described as a manifold with a well-defined metric that is not describable in terms of Riemannian geometry. Let's call this definition D1. Some say that a non-geometric background is a background where T-duality transformations are required to make the background well-defined. We will mention what this means later. Let's call this definition D2. Some people employ a stricter definition as follows. When we apply T-duality to a background, GB and phi, it changes in a non-trivial way to another background, G', B', and phi', called the T-dual background of GB and phi. Now, some say that a background is non-geometric if T-duality transformations are required to make the background well-defined, but it is not T-dual to any background that can be described in terms of Riemannian geometry. Let's call this definition D3. We now mention what we mean by a well-defined background. When we study curved spaces, we don't label the whole space with a single coordinate system. Instead, we employ patches to cover this space, and in each patch, we have one coordinate system. But these patches can overlap, and thus, a single point can be a part of multiple patches and thus have multiple coordinates. How are these coordinates related? They are related by something called transition functions. For geometric objects, these transition functions are ordinary continuous transformations called diffeomorphisms. A similar reasoning takes place when, in addition to coordinates, we define fields on a curved space. They are also defined in patches, and at a single point, we might have more than one patch, and thus more than one value of a field. These values are also related via transition functions. Now, consider the background, GB and phi, defined over a curved space. If the transition functions for these fields are given by T-duality transformations, We say that T-duality transformations are required to make the background well-defined. So, are there any examples of such non-geometric backgrounds? I will present just two related examples. A well-known example is a three-dimensional torus, called a 3-torus or T3, with a constant H field and its T-duals. H field is the field strength of B field just like F is the field strength of the ordinary EM field. H field is also called H flux. T3 with a constant H field is a geometric background. It is easy to see that T3 has 3 circles in it. We can do a T-duality transformation along one of these circles. Then we get something called a twisted torus, and the flux that we get on it is called the F flux. This is also a geometric background. The F flux is called a geometric flux, as it has a geometric interpretation. Actually, it can be seen as structure constants of an algebra. Now, we can perform a T-duality transformation along another circle, and this time, we get something called a T-fold. T-fold is non-geometric according to definition D2 above, because we need T-duality transformations to make G, B, and phi well-defined here, but not according to D3, as it is T-dual to the twisted torus, which is geometric. The flux that a T-fold has is called the Q flux, and it is a non-geometric flux because it lacks a geometric interpretation. Requiring T-duality as transition functions is a thing that happens when two patches overlap. But what about the description within a patch, where there are no overlaps with other patches? There is nothing non-geometric about T-folds within a patch. We say that T-folds are locally geometric. Can we do a T-duality along the last remaining circle? Well, not in the usual way. This is because to perform T-duality along a circle in the usual way, translations along that circle should be an isometry, which means that the metric should not change under those translations. However, the metric G for the T-fold isn't invariant in such translations. This last T-duality can still nevertheless be performed in an unconventional way, but I won't explain that procedure here. I will only present some features of the resulting space. The resulting space is called the R space, and it has a non-geometric flux called R flux. R space is even more non-geometric than the T-fold, because it isn't geometric even locally. Arguments can be given that suggest that the concept of a point doesn't make sense for R space. I will postpone these arguments for a later video. We don't understand R space very well. Interested viewers can read this review or read these original papers. Thanks for watching. If you liked this video, then give it a thumbs up, and if you like the content on this channel, then consider subscribing. Thanks and have a good day.